Okay, then let's continue with functions and DPUs.
Hey everybody, my name is Tim Rose. I am a maintainer for the Oven Kubernetes project. If you can't tell by my cool shirt I've got on. And I'm going to be talking about service function chaining, data processing units, and shared oven. So some of you might know something about each of these things, but maybe not how they're related. So I'm going to start with service function chaining and then move to DPUs and shared oven. And by the end of this presentation, hopefully you guys all understand how they all fit together. So what is service function chaining? So I've given a link here to the RFC 7665. And from the RFC, the definition is the instantiation of an ordered set of service function, and the steering of traffic through them is considered to be a service function chain. So in practical terms, you can think of a service function chain as an ordered list of network functions that traffic goes through. So like in any traditional routing appliance, you have an ordered list of network functions that traffic goes through, like ACL, NAT, firewall, load balancer. You can even think of the pipeline with Oven as a type of service function chain for its ingress and egress pipelines. To go into a little bit more detail about service function chaining, so as I mentioned, it's a logical sequence of service functions. You have classifiers that match on packet headers to put the packets on specific chains, so those can match on different things like different parts of the packet 5-tuple. The centralized control plane defines service paths for service function chains, and the data plane enforces them. Service function chains can span multiple nodes or domains. Service functions may also be aware of the service function chain. So as a packet comes into a service function, it may be aware of the service function chain itself using metadata and encapsulation information. It also allows for load balancing across multiple instances of the same network service. So if you have, like as we saw in the previous presentation, which is a good segue into mine actually, if you have multiple of the same CNF or VNF, you can load balance across them. Packet headers may be modified as the chain is traversed. So things like a NAT might modify an IP address. Other parts of the packet may be rewritten depending on what your service function is. So here's a simple example. I'm going to try and be as simple as possible with all the diagrams just so I can get my point across. But we're going to build up slowly. So here we have a diagram with two service function chains. You have a service function chain that includes service function 1 and service function 2. And then you have a blue chain there on the bottom, which is a single service function chain using just SF1. So SF1 here is participating in two service function chains. So as a packet goes from the client with the black arrow into the first chain, hits service function 1, it then gets load balanced down into service function 2. There's two instances, and then it goes to server 2. And the other service function chain is where the client sends to service function 1, and then it goes to server 1. So here's a service function chain example with multiple nodes. So in this diagram, you can think of this as two different Kubernetes nodes if you want to. It's two different nodes with OVS on them. We have a client and a server, and then I've shown in steps how the packet is traversing. So the client sends a packet towards a service function forwarder. So a service function forwarder is basically something that understands, it's basically the data path that understands chain information. So it knows, it's aware of chains, it knows how to get packets to different SFs within each chain, and we're going to call that for our purposes OVS. So OVS is acting as a service function forwarder. So the client sends the packet in step 1, service function forwarder forwards it down to service function 1, it then comes out into back to the service function forwarder on node 1. Step 4, it goes across to the other node, to the service function 2, service function 3, comes back, and then the service function forwarder sends it back to the original node, and then finally to the server. So why does service function chaining matter? So it allows you to have dynamic service insertion. So you can create your own chains, and you can dynamically create them. They're not hard-coded like a traditional router pipeline or like Oven's pipeline is today. And you can inject or insert whatever service you want, compose whatever service chain you want. It also overcomes some of the limitations of OpenFlow. So with OpenFlow, you can only match up to layer 4. And like with layer 7, obviously, we can't do that in OpenFlow. So it allows you to insert your own service function that's able to do that. Some people that are running their platform would like to choose a different appliance to use as their network function. So maybe they don't want to use, for example, Oven's built-in NAT functionality, and they want to use their own. And it's granular, so it allows per flow, per tenant, per application network pipeline. So you can match on different parts of the 5-tuple and put packets that are different onto different service function chains. Okay, so what is service function chain symmetry? And so I'm touching a bit on the service function chaining fundamentals so that I can show a solution kind of in the end. So symmetry is basically just the fact or the option with service function chaining to have the reply path be the reverse path of a service function chain. So if you have a chain that's ABC, then the reverse path would be CBA. So how symmetry can be achieved, one way is to create a reverse chain and an inverse classifier. So if I created a chain ABC, I'd create a chain CBA. And then if my classifier, for example, was to match on destination port 80, I'd create a reverse or an inverse classifier to match on TCP port source port 80, so that the traffic will go back the same way. Symmetry can also be achieved using stateful tracking like contract, and that was done in the previous presentation, as you guys saw. And what is SFC metadata and encapsulation? So data plane encapsulation is a way to be able to carry information about the chain between the service function forwarders and also to the service functions themselves. So as I mentioned before, the service functions can be SFC aware, and using this encapsulation or metadata allows you to carry that information towards the service function. One implementation of this, which is the only real standard, is called Network Service Header. And there's a link to the RFC there, or NSH. And how that works is when the packet basically gets encapsulated with another header, that header is then sent off towards the service function, and it's used between service function forwarders. And we can go into that a little bit later if I have time. Other implementations like OpenStack with ML2 OVS use MPLS instead to carry that metadata. So why is metadata necessary? So it allows you to know what chain the packet is actually on at a time. It allows you to know where in the chain it currently is with the service index. So with NSH, when a packet is going through a chain, it starts with a service index of 255, and it decrements by 1 for each service function it goes through. So when a service function receives the packet, it knows how many other service functions it's gone through. So you can protect the integrity of the chain. You also know who is sending packets through the chain. So you can put in metadata about the tenant ID, or you can know the original node that sent the packet. And you don't have to use metadata. So some service functions are not NSH aware, obviously, most aren't actually. And so you can use proxying, where the service function forwarder strips off any encapsulation information and then proxies the packet over to the service function. So this is the same diagram I showed before, but now we're going to walk through some of the problems if you don't use any metadata at all. So we have the client, as we said before, sending the packet into the service function forwarder. It goes to service function 1, and then when it comes out of the service function, the question is how do you know which chain this packet belongs to? Because service function 1, as I showed in the first example a while ago, service function 1 could be a part of multiple chains, right? So when the packet goes into service function 1 and it comes out, you have to know which chain it's on so the service function forwarder knows where to forward it next. So without metadata, that's not possible. The only way we can do it is if we consider service function 1 can only be part of a single chain at a time. And then when the packet comes across between nodes, so the service function forwarder is sending it over to the one on node 2, when the packet arrives, how does node 2 know which chain this packet belongs to without any type of metadata? So it doesn't. And then after the packet goes towards service function 2 and service function 3 and comes back up, how does node 2 know how to send it back to node 1? If there's no metadata, it's not able to know which origin node to return it to. And that's where something like the contract stuff comes in handy. So how can we adapt service function chaining to Oven? So these are some of the things I've thought of. We've had some discussion on the mailing list, and this is kind of the outcome of that. So because we don't want to have, as a starting point, we don't want to make things too complicated. So as the first point here, I've put to support unaware SFC unaware SFs, so not having to support NSH or anything like that. We can use Geneve to pass metadata between nodes. We can have chains that span multiple nodes without packet modification. So both of these 2 points are akin to the presentation that was just given. So we can use the same methodology. If we want to allow packet modification support for some service functions, that chain must be contained within the same node, because otherwise we would have no idea when that return packet comes back what chain it was on. A service function may only be part of a single chain, as I talked about before. Without metadata, we wouldn't know when the packet comes back from the service function which chain it was a part of, so we need to restrict it to only one chain. And we can allow for load balancing across multiple instances of the same service. The other thing that I really want to achieve is to support hardware offload. So based on the previous presentation, how can we extend that to do service function chaining? So in the previous presentation, you heard about the network function group table. And so here, I didn't realize that they had already updated it to use active-active for load balancing. So that's good. So that already solves this first problem here. I wanted to be able to do that. And then they had introduced a ACL reference to the network function group. And so I'm proposing here to introduce a new reference to a new table called service function chain. And the new service function chain table would hold references to network function groups. So a network function group would be a container that holds one or more of the same type of service function. And then in the service function chain table, you'd list a ordered list of NFGs, and that would describe your chain. And down here, I have a link towards the discussion we've already had about service function chaining on the mailing list. So this is just like a quick prototype I threw together just to have a visual. So this is what I prototyped the service function chain table to look like. There's a mode here with local and immutable global. And here you would list your network function groups in an ordered list. And so the mode local would not use contract, and it would allow for packet modification within a node. Oven would check that all the NFs that are part of that SFC are bound to the local chassis. And in this mode, symmetry is not implicit, so the CMS would need to create a reverse classifier or an inverse classifier and a reverse chain to achieve symmetry if you want to. With the immutable global mode, it would use contract, similar to the way that's already being proposed in the network function group spec, but it would not allow for packet modification. You could still use this immutable global mode if you only have a service function chain and it's within a single node. And in the future, I thought we could extend it later if we want to add support for NSH or some other data encapsulation that would allow you to do like full packet modification as you traverse nodes. We could create a new mode. Obviously, maybe these names are not great, but it's just to get the point across. So now we kind of move to Oven Kubernetes and service function chaining. So in this is a picture of a worker node in Kubernetes. We have Oven Kubernetes, which listens to Kubernetes events. It programs Oven. Oven configures OpenFlow down in OVS. We have a pod A and a pod B here on the left-hand side connecting to a worker logical switch. So inside of this OVS container, I've tried to represent things as Oven logical entities. So you have pod A and pod B. You have a SFC logical switch, which is attached to our network functions, a layer 7 firewall and a layer 7 load balancer. You can imagine there's some chain like pod A sends traffic and it needs to go over to the layer 7 firewall, then the load balancer, and then go to pod B. All right, so now let's segue into DPUs. So what is a DPU? So it's a specialized programmable networking security accelerator designed to offload work from the host CPU. Basically, it's a smart NIC with its own CPU, memory, OS, and hardware accelerators. So this is what the Oven Kubernetes topology looks like with the DPU. So we have the same host as before. All the pods are on the host. And now we have a DPU, which is our smart NIC running down here. And you can see what we've done is we've shifted all of the SDN components down into the DPU. Now, there are components here missing, but I wanted to make this as simple as possible for this presentation to just get the point across that our SDN control plane and our data path are both moved down. So now our pods are wired to OVS using VFs and VF representers. Everything is down here. Otherwise, the OVS is down here with our worker logical switch and our service function logical switch. So what does that give us? So it gives us hardware offload because now we're using VFs. It reduces resource consumption on the host because now we've moved all of the Oven and Oven Cube components and OVS down to the host, down to the DPU. Of course, that comes at a cost because now we're using more DPU resources. And we improve security. So if we had, let me see if I can go back here. So if we had all of these components up here, and let's say that in Oven we are using, if we were using something like an ACL or egress firewall to stop these pods from being able to send traffic out onto the external network to some server. If pod A breaks out, it could manipulate OpenFlow if OVS was running inside of the host, or it could manipulate Oven. By moving things down into the DPU, when these pods break out, they cannot they cannot compromise the SDN because they have no way to get to the DPU. There's no Unix or TCP socket or anything they can leverage to get into it. So it provides that extra layer of security. So what if we were to also install Kubernetes on the DPU and use Oven Cube and Oven there as well? So that would look something like this. So now we still have the same exact host, and I'm calling the Kubernetes cluster that's installed on the host as the K1 Kubernetes cluster. And now down here in the bottom, we have the DPU, which is the K2 Kubernetes cluster. So I've installed Kubernetes across all my DPUs as well, and that's represented by all the blue stuff. So now I still have my Oven Cube down here that was running before for my K1 cluster, and that's handling wiring these pods A and B to my worker switch. And then on the right-hand side, I have Oven Cube that's installed for K2 on the DPU cluster, and it's configuring this SFC logical switch with the layer 7 load balancer and the layer 7 firewall are now running on the DPU. So those are actually pods that are launched on the K2 cluster as part of the DPU itself. So the question is now, if I want to do service function chaining, how do I get traffic from this switch, which is really going to be represented as a different OVS bridge, over to this switch, which is another OVS bridge because it's being managed by a different oven stack. So there are ways to do that. You could allow Oven Cube K2 to be able to configure parts of Oven K1 to make that happen and have a patch port between the bridges. We don't really have an answer for that yet. That's something we need to figure out. And so what does this give you? So if we consider that the DPU is installed by an admin and he's the one creating the service function chain because he wants to protect traffic that's sent out of the cluster, it gives you security at the edge. So now the entire chain is down here inside of the DPU, and anytime these pods try to send traffic, they're forced to go through the service function chain. There's no way that the pods can compromise the service function chain, and it brings your security down into the DPU and enforces it there. So what if we were to combine these ovens into a single shared oven? So now you can see where this is all going. So now in this diagram, we used to have an oven for K2 and an oven for K1, and now I've combined these ovens into a single shared oven. So now we have the K1 Oven Cube and the K2 Oven Cube. They're both programming the shared oven. The Oven Cube for the K1 is able to read and write things for its host that it needs to create, like its worker logical switch. And the Oven Cube K2 serves more of an admin role. So while it can configure the SFC logical switch and all the things it needs for the pods on the DPU, it can also read and see things that are created by K1. And so it can inject ACLs to say you should redirect packets towards that service function chain. So here are some of the advantages. So as I mentioned, the K2 cluster has admin RBAC. It can modify entities within the host cluster, allowing it to inject ACLs. The K1 cluster is only allowed to see its own contents, and it's not able to configure or change the ACLs configured by K2. So the question here is Oven RBAC secure enough? So one of the issues is if someone were to compromise the Oven K1 cluster. So let's say that, obvious one is they try to alter like the ACLs or something that the Oven Cube K2 installed inside of Oven. That's one way they could try to attack. Another way they could attack is we've seen bugs before where there's some type of misconfiguration in the northbound DB, and that triggers NorthD to be able to stop processing. So like could Oven Cube K1 be manipulated so that you could inject some invalid config that would halt NorthD or Oven controller from being able to render stuff? Those types of things. So that's something we need to figure out. And then the other thing is, does running a shared oven model actually reduce resource consumption? So by combining the ovens into one, do I actually reduce my CPU usage or my memory footprint? And we don't really know yet. So the next steps are, I want to move this thing forward with service function chaining. So I need help from the oven community, whoever's interested. And I think it's worth building off of what's already been done by the Nutanix folks. And so I want to target a single cluster with service function chaining with Oven Cube first, make sure that works and get upstream testing done for that. And then I want to move to trying to test a non-shared 2-cluster model, while in the meantime, we do perf scale and security hardening to see whether it's worth trying to pursue shared oven. That's it. Any questions?
Thank you very much. Do we have questions in the round?
I would be just interested, what's the timeline you would like to see that happen in OVN, I guess?
I don't really have like an urgent timeline for it. It's just I just don't want it to die out. So yeah.
Okay, thanks.
Yeah, you said you are going to allow packet modification in the network function in the service, right? So in that case, let's say if it is doing some TCP sequence number mangling, some of the firewalls do that. So how do you plan to handle that when the request goes from X to Y and it is redirected and it changes the sequence number from some A to B? Response comes with acknowledging B, right? So the this guy will now drop the packet because it doesn't know about that sequence number. Are you planning to allow that when you say packet modification is allowed?
So when the packet flows through the chain, we know the ports that we know it's local, and we know the ports that it's going in and out of, and those service functions can only be a part of that single chain. So all we need to know is in and out port for delivering it through the chain. And then on the reply packet, you have to create your own inverse classifier to be able to put it back through the chain in the right order, because we don't have stateful tracking in that scenario.
Okay. Yeah, maybe as long as you have thought about, because the way we described is response packet will directly come to the destination where it is supposed to, and then it will take a U-turn and go back, right?
Yeah.
So in this case, if sequence number is different, is unexpected, it might drop it.
Yeah. So you might not want to use symmetry is one option. So you might not want the reverse flow to go back through the chain. But if you do want symmetry, then you have to define that classifier and service function chain in the reverse order yourself, because there's no way we can contract at that point, right?
Right.
Yeah.
Do we have more questions? There's one here.
Just a simple one. How does a DPU look like from the Kubernetes standpoint? Like a regular node, or?
Oh, so
Because I assume that's a
it sounds like a simple
that is attached to a regular chassis.
Yeah, it sounds like a simple question, but it's not a simple answer. In this mode, in the mode we support today, it doesn't act like a separate node. So it acts like it's part of the Kubernetes node.
Okay, so you basically kind of assign node resources, node special resources to some of those pods, right?
Yeah. Yes. So okay. So in this diagram where the DPU is launching pods, it's considered a separate node. Yeah.
Right. Cool. Thank you.
Now that we're on this diagram,
I'll change it. Hold on.
no, it's, without shared oven, how would you connect the two switches? You mentioned patch ports.
Mm-hmm.
And on your last slide, you said you don't really want to look into shared oven yet. So what's your plan then? To use patch ports as an intermediate first solution, or?
That's what I was thinking, but I need help from the community. I need your expertise.
Maybe you can add an item on the next OVN community technical meeting. It's in 2 weeks, I think.
Okay. We can
discuss some more there.
Okay.
Thanks.
Yeah, thanks.
If there are no further questions, then thanks to our speaker.